Now let's zoom out for just a second and get a feel for if we are an engineer and we're trying to take measurements, what is important to us? Well, we've got a finite number of resources or money, and maybe we've got a finite number of samples. Maybe they came from outer space, and so we have 5 samples and we can't get any more. Or maybe they're very expensive to manufacture, or maybe we need them because we're making money off of each one, and so we can't destroy anymore. So there are different reasons why we would need to spend different amounts of money to get good data. And so if we zoom out for just a second, we look at instruments and their performance specifications. A lot of times they will fit into these categories: accuracy, precision, resolution, sensitivity, and hysteresis. And so if you look at the accuracy, the difference between the measured value and the actual value, generally reported from vendors as maximum error. So this is like if you buy a pressure transducer and they say it is good to 5% or 0.05%, that is the accuracy. Now the precision is the difference between the instrument's reported values during repeated measurements of the same quantity. Resolution, smallest increment of change that can be measured in the value that can be determined from the instrument's readout. So it's usually similar to or smaller than the precision error that you see. Sensitivity, the change in the output of an instrument per unit change of the input. So how sensitive this piece of equipment is to the input that's going into it, or the signal that we're trying to measure. And then hysteresis, that means a lag between the input and the output of the system upon change in direction. So we're going to look at through all these, but one quick important note here is that the resolution is typically considered a bias error. Okay, so that's going to come into play later on. So precision versus accuracy. Precision is the smallest number that can be repeatedly reproduced by a measurement system. So the precision is not the same as the accuracy, right? So if we have a highly accurate system without any precision, we're going to have a wide scatter, because that precision, we're going to have a lot of randomness in our data. But if we had precision without accuracy, that means we're going to have a very tight grouping, but it's going to be off. So we've got a small random error, so the randomness is small, but we have a significant bias. So if we had both accuracy and precision, now we've got a nice tight grouping, and it is right near the true value that we're trying to measure. So if we have a distribution of errors, and we look at one of them, we take this top left corner and we say, all right, let's take a slice through here and rotate it on its side. We've seen a curve that looks like this in our past. And a lot of times we will call this a bell curve, a Gaussian distribution, normal curve. And we are going to become very good friends with this curve here. And the reason for that is because you can see we've got some bounds here. We've got plus and minus z, and we have a confidence percentage. So if you think about it, if we take a whole bunch of samples and we do a slice here, now we're looking at this might be the average or the true value that we're trying to measure. And if we have a confidence, we have now put bounds on it. So now we have the uncertainty. We can say, we are very confident that if you use our device or use the material that we selected, we are very confident that you are going to have a data point that falls within this range or uncertainty or confidence interval. Confidence interval and uncertainty are the same. Okay, so if we look at that and we look at a couple of different scenarios, we've got our precision without accuracy, like we're talking about here. So we've got an offset, a bias. So we've got this bias error that's offsetting every single value. But look, our precision error is pretty small. So it's nice and tightly grouped, but it is off of the true value by quite a bit. And so we've got our total error, we've got our bias, plus our precision. Holy smokes, we're getting back to the original problem that we started with. We're getting back to knowing and understanding what our total error is, or total uncertainty. So if we do the same thing with the accuracy without precision, you can see we are very close to our true value. And so our bias error is very small, but our precision error is very large. So the Gaussian distribution is now stretched out. It's much wider. So now the total error, we've got our precision and our bias error, and they're combining to be this total error. which is what we're after. So I just wanted to make one quick comment. Hysteresis, a lot of sensors have an undesirable characteristic of giving a different value when the input is increased when it is decreasing. That is called hysteresis. So if we go up on this side, a lot of times you will have a different value on your way up. And so on the way up, if you start loading something or you change your input value, that sensor is going to have an output on the way up that is different than on the way back down. And so that difference there is hysteresis. That's going to be a problem for us.
All right, so trying to put a few things together here. We've kind of talked about error and uncertainty, the difference between the two, and also the relationship between the two. We've got errors that cause us to not know the true value, and then we've got uncertainty, which is essentially a numerical bound that says we have a certain degree of confidence that every time we measure something, it's going to fall within this grouping between this low level and this high level. And so it kind of quantifies our error. So going back to the original concept here of overall uncertainty, we want to figure out what is the total uncertainty that we have, or how good is our measurement? How good is this measurement? How confident are we in this measurement? So the overall uncertainty is going to have a combination of both the bias type of uncertainty and the precision uncertainty. But before we combine those two, a lot of times, if we can define what the bias is or what's causing that shift away from the true value in a systematic fashion, if we can define what that bias is, a lot of times we can take it out. Otherwise, if we can't take it out for whatever reason, then we need to model it as an uncertainty in the overall equation. So the overall uncertainty, instead of just taking the bias plus the precision, because we have some plus and minus signs in there, we'd have some things canceling out. We need to do the root sum square of the bias and random uncertainty and other classifiable errors like hysteresis and calibration and others. So this equation right here, equation 3.4 from the book, this equation, you can imagine we're going to have a lot more terms than just one bias and one precision. We're going to have several bias, several precision. But the concept of taking the root sum squared is what we want to get across at this point. So your total uncertainty is going to be the bias squared plus your precision squared and then the square root of those. We're going to see this equation a lot throughout the next few sections. Okay, so just to recap, uncertainty in an engineering context is defined as the margin of error of a measurement, such that an interval encloses the true value with an associated probability. So we're saying the true value, the thing that we're trying to measure, is going to fall within these intervals. So we're capturing that true value within some intervals, and we're going to say there's a probability associated with us capturing the true value. It encompasses both precision and random errors, precision / random errors, and the bias / systematic errors. So again, going back to that equation 3.4, the probability that an uncertainty interval where the resultant bounds encloses the true value is referred to as the confidence associated with the uncertainty. So confidence and probability, we're kind of tying some more terms. And I know there's kind of a lot of new terms here. We've got the precision / random, we've got the bias / systematic, and then now we have probability / confidence. But these, as we work problems and as we talk through it, these are going to become a lot more concrete for you to understand. But just think of confidence is the probability that something's going to occur within that range that we give to. And it's generally referred to as a percentage. So a lot of times we're going to say our confidence is going to be 95% or maybe 99%. And so essentially that is the probability that the true value is going to fall within that range.